Hello and welcome to the third video, Identifying Variables. I'm Mrs. O'Neill. This video is intended for the physics class at Goessel High School. This is video 1.3. What science always comes back to is data and data analysis. We're looking for patterns in the numbers that surround our lives. So just to recap, data is defined as being a collection of measurements, and these measurements have to have numbers and units in order to be data. Sometimes they have direction as well, but they're required to have the numbers and units. The type of data analysis that we can perform depends entirely on the type of data that we have available. For example, if I give you a problem with time and mass, you can't use that to calculate velocity, because to calculate velocity you have to know time and distance. We define this data into categories called variables. So variables are categories of data. There's two major types of data. It can be scalar variables, if we only have magnitude but not direction, or they can be vector variables if we have magnitude and direction. So for example, scalar variables are going to be here, vector on the other side. Sometimes they come in pairs. Like for example, it's called distance if you don't have a direction, for example 11 meters, and displacement if you do, 11 meters due west. So distance is scalar, displacement is vector. This is also the difference between speed and velocity. Speed is scalar, velocity is a vector. Acceleration, on the other hand, always has to be a vector. It has no scalar equivalent, and time is always scalar. It doesn't have a vector equivalent. Often we don't like writing out directions longhand, like this due west stuff, so we're going to be using positive and negative signs a lot to indicate what direction things are moving in. We're going to go into this in a lot more detail in a future video, so don't worry about it too much today. Alright, we use these variables in our physics formulas. Each variable is assigned a symbol. Usually it's a letter, sometimes it's two letters or a combination of Greek letters and English letters. So, but they have different, each of them has, anyway. Many physics equations actually don't have any numbers in them at all, only these symbols. And then we need to plug in our numbers into the correct spots. There's going to be 4 variables we're going to see all the time in this unit, this kinematics unit. For example, delta x is a variable that stands for displacement, and the unit is going to be a distance unit, such as meters or centimeters or kilometers, stuff like that. Delta t stands for time, and that's going to be measured in seconds or minutes or hours or whatever. V is velocity, which is a distance over a time, meters per second, kilometers per hour, stuff like that. Or A for acceleration, which is distance over time squared. For example, meters per second squared, kilometers per hour squared. Those would all be acceleration units. This triangle here is not a triangle. It's actually the Greek letter delta, and it just means change in whatever it's preceding. So delta x here is change in x, which means change in location along the x coordinate axis. Delta t is change in time. So that Greek letter delta is going to pop up a lot. Alright. We also sometimes further differentiate our variables by using subscripts. Often we have two of the same type of data that come from 2 different times or 2 different locations, and so we use these subscripts to distinguish between different types of the same variable. For example, a subscript I stands for initial, and you'll see stuff like v sub I for the initial velocity, and it's always pronounced just v sub I. A subscript f, on the other hand, means final, and you might see v sub f, final velocity, v sub f. You can have initial acceleration, final acceleration, initial time, final time. There's all sorts of different ways that this can be used. Okay, now for the bad news. These physics problems that we're going to be solving are almost always word problems, because a word problem can be used to describe a real-life phenomenon, which is what physics is all about. So the first thing we have to do is pull out of this paragraph, the written word problem, what variables are being given. What kind of data do we have in this word problem? So that's our very first and actually most important task, is to identify the correct variables. In order to keep this tidy, once you know what they are, we're just going to write them down beneath the word problem in a nice neat column on the left-hand side. In order to identify variables, we have to pay close attention to the units. The unit tells you which variable you're actually looking at. Let's look at an example. Here's a word problem. Morgan rides her bike 1.2 kilometers to school every day. It takes her 15 minutes to get there. How fast does she go? We're not going to try and solve this yet, but today we're just practicing identifying our variables. The first thing we want to do is just pull out the numbers. 1.2 kilometers, 15 minutes. Then we need to think to ourselves, what kind of a unit is this kilometers? What kind of a variable is this? Well, kilometers is a distance unit, and so our variable here has to be delta x. Delta x is 1.2 kilometers because delta x is our distance. 15 minutes, well, minutes is a time unit, so 15 minutes has to be our delta t. So there we have it. There's our two variables from this problem. Ooh, let's do something harder. Rick drives to school. He pulls into the parking lot at 15 kilometers per hour and then slows to 6 kilometers per hour in 0.1 hour as he crosses the speed bumps. How quickly did he lose speed or decelerate? Well, in this case, we have three numbers, 15 kilometers per hour, 6 kilometers per hour, and 0.1 hours. Sometimes it's helpful just to sort of maybe try and sketch this out. He's driving at 15, then he slows to 6, and it takes him this long. So this is actually his initial velocity, v sub I, because he's starting at 15 kilometers per hour. Then he's ending up at 6 kilometers per hour, that's his final velocity, and the 0.1 hour, that's delta t again. So we did it again, we figured out our variables. There's one complication, sneak words. Often, the data is given in the phrasing in the problem instead of being an actual number written into the word problem. So not all data is in the form of numbers. Sometimes it's hidden in the words, the language being used. So you have to read carefully. We call these sneak words. They're giving numerical information, but not in a numerical form. Some of the commonest ones that we're going to see, if it says that something is occurring from rest, or from parked, or from neutral, or from a stop, or whatever, that means its initial velocity is 0 meters per second, or some other velocity unit. It could be kilometers per hour, or whatever. On the other hand, if the problem says that something came to a halt, or came to a stop, that means its final velocity is 0. So we're not just looking at our numbers here. We're also trying to read carefully to see if there's any of these sneak words in the problem. Alright, let's look at one last example. Gloria jogged briskly at 2.5 meters per second. Spying a lost puppy, she drew to a stop by slowing at negative 0.8 meters per second squared. How long did it take her to stop jogging? So girl's jogging along, spots a dog, stops. Pretty simple. First thing we want to do is pull down our numbers, 2.5 meters per second and the negative 0.8 meters per second squared. These are obviously data. It's a good idea to try and identify what type of data they are. This meters per second is a velocity unit, and this is describing her initial condition. She's jogging. This is what's happening first. So this is our v sub I, 2.5 meters per second. This meters per second squared is acceleration. The squared is always a dead giveaway for that. So that's our acceleration, negative 0.8 meters per second squared. But there's one other piece of data that's sort of hidden in this problem. And that's right here, where she says she drew to a stop, because when you draw to a stop, your final velocity is 0. So that's the last thing we know. There's actually 3 pieces of data in this problem, not just 2. Alright, that's it for today. We're just trying to figure out how to identify variables. Don't forget to take the video quiz. The link is in the video in the description below. And don't forget, you need to be logged into your school Gmail, enter the correct name in order to access the form, and make sure that I get it in your name. Thank you for watching, and I look forward to seeing you in class again sometime soon.